Let's look at the following example. So let's assume x and y change together such that the change in y is negative 0.6 times as large as the change in x. And this means that there's a constant rate of change of y with respect to x. And it also tells us that when x equals negative 2, y equals positive 2. Now, this applet that's provided to us allows us to vary the current value of x, and as we do that, the changes in x and y are represented graphically using vectors. Then on the right-hand side, we're given the current value of the change in x and the change in y, as well as the ratio between these two changes. What you should notice is, given any change in x, so if we look at the change in x, the change in y is always going to be negative 0.6 times as large. And visually, this should make sense. Our axes are to scale, so we can look, and if we look at this change in y, this change in y appears to be about negative 0.6 times as large as this change in x. Now you can also confirm this numerically. If you look at the change in x and the change in y, and you compute the ratio, that ratio is always going to be equal to negative 0.6. Now we can use this information to actually answer some questions about how x and y vary together and compute some new values of y. So we'll look at this next prompt. We can think of negative 2, 2 as our reference point. In other words, we can think about the initial value of x being equal to negative 2, the initial value of y being equal to positive 2. We'll use the applet to change the value of x to x equals 4, and we'll look at what happens to the value of y. So if we go back up to the applet and set x to about x equals 4, we notice that the current value of y, we're going to approximate that to be a little less than negative 1, so maybe negative 1.2. We'll actually compute that value here in a second. So if we scroll back down to the question, when x changes from negative 2 to x equals 4, what is the change in x? We know that the change in x is going to be equal to the final value of x, which is 4, minus the initial value, which is negative 2. And notice that MathAS is going to compute this actual value for you. So if you type in this expression, it'll actually tell you that, okay, 4 minus negative 2 is equal to 6. So you can use MathAS like a calculator. Now for this change in x, we know that the change in y has to be negative 0.6 times as large. So the corresponding change in y is going to be negative 0.6 times as large as the change in x, and the change in x was equal to 6. So the change in y is about negative 3.6. Now the value of y when x equals 4, now if we want to compute the new value of y, we know that this new value of y is going to be equal to the initial value of y plus however much y changed by. And we know that the initial value of y, so if we look at the initial value of y, we knew that that value was 2, and we just computed that the change in y was negative 3.6. So if we plug those in, an initial value of y of 2, a change in y of negative 3.6, then that tells us that our value of y when x equals 4 is 2 plus negative 3.6, which is negative 1.6. So we were close when we approximated graphically. And if we submit this, we see that our answers are correct. So we can go through the same way of thinking for any value of x. So let's see what happened when x decreases. Let's imagine x varying from negative 2 to x equals negative 5. So what we imagine happening is if we had a number line representing the value of x, we have 0, -2, -5. What we're going to imagine doing is we'll imagine x varying from -2 to 5. And since our value of x decreased, we expect our change in x to be negative. You might be able to eyeball this as change in x equals -3. And in fact, if we compute the final value of x, -5, minus the initial value of x, which was -2, that change in x is -3. And we know that the change in y has to be -0.6 times as large as this change in x. So the change in y is going to be -0.6 times -3. So this change in y is about 1.8. It's actually exactly 1.8. iMathAS just has some rounding errors every now and then. So the value of y when x equals -5 is going to be equal to the initial value of y, which was 2, plus however much y changed by, which in this case was 1.8. This tells us that the final value of y is whatever the value of 2 plus 1.8 is. And that value is equal to 3.8. So if we submit this, we get green boxes. Now, for the final two examples, you can use the same way of thinking and just imagine x varying from some initial value. So you imagine x varying from the initial value to some final value, and you can always compute the change in x as whatever the final value of x is minus the initial value of x. And in this example, we know that the change in y has to be -0.6 times as large as delta x. So -0.6 times as large as your previous answer. And to compute the final value of y, we know that the final value of y is going to be the initial value of y, which was 2, plus however much y changed by. So in this case, it's going to be -0.6 times as large as delta x.